The DRlearn team offer education and training in the world of heat pump technology and other energy efficiency areas. Professionals from the industry interact and educate participants looking to learn more about the design, operation, and maintenance behind residential and commercial heat pump water heater systems. The educators and designers on the Learn team offer an extensive catalog of courses and trainings for live instruction or self-paced online learning. Enjoy a portion of one of the live training seminars in this video and contact the Learn team to discover opportunities to train and educate your team and customers.
All right, yeah, so we're getting ready to jump into the evolution of heat pump technology and just talk about where our heat pump systems derive from, where they came from, how they came to. So that way we have a general understanding of heat pumps and a little bit of its history. So this will be a bit of a history lesson here, but I find that it gives you some baseline to understanding heat pumps, where they came from, and looking at that evolution up to where we are today. So for some of us, I know we've got a tech in here that has about 20 years, but I'm sure that individual knows this as well. But heat pump technology is a new technology. As a matter of fact, it has been around for some time now. Now, looking back a few years ago, the first heat pump was introduced in the 1850s by Peter von Rittinger and later developed by Lord Kelvin and James Joule. Kelvin, Joule, coming together? Not yet. All right. Robert C. Weber patented the first practical and commercially successful heat pump in the 1930s, paving the way for what we have now, which is the modern heat pump system. Now, if we take a look up in the top left-hand corner of our screen, we can see a refrigerator or a unit looking like a refrigerator up there. This system was known as the GE monitor top refrigerator, and it played a vital role in the development of heat pump technology. Now, this cute little refrigerator dubbed the GE monitor top was introduced back in 1927 and was the first widely successful home refrigerator. If you look on the top of that, you can see something golden there. This was a hermetically sealed compartment which utilized the heat pump system to circulate refrigerant and extract heat from the interior of the refrigerator. Now, the heat that was extracted was then expelled outside, leaving the refrigerator cold and the contents stored inside of it preserved. The compressor for this refrigerator was mounted on the top of the unit, and a fun fact about this is that the unit quickly gained the name monitor top because the top-mounted refrigerant compressor resembled the gun turret on the Civil War ironclad ship named the USS Monitor. So just a little bit of history there for you on one of the first refrigerators utilized in residential applications. Now, as that technology got better, and we did talk about this a little bit earlier, we're going to bring it up, heat pumps began to be incorporated into everyday life and different pieces of equipment. Let's take a little minute here to explore this image in the middle, which is the Schultz-Sherman room cooler. If you take a look at this image, you can see through the window there's a gentleman in a short sleeve shirt sweating like he's had the worst day ever. And that tells us that it's probably pretty warm outside. But if you take a look inside this home here, you can see everyone's pretty dressed up. You've got a gentleman back here with a suit on, and it tells you a lot, just looking visually at this image, that there's something in here keeping this environment cooler than it is outside. And it is that box that you can see there near the window separating the individuals in this image. Now, in 1930, John Schultz and Raymond Sherman developed a heat pump system for residential cooling called the Schultz-Sherman room cooler. And this system was used as a heat pump to cycle and transfer heat from the room to be cooled and expel it to the outside, resulting in a much more cooler indoor environment. So we can see there that we started implementing this heat pump technology into zones or residential applications where we can now cool larger zones bigger than this little space that we could see in this refrigerator to the left. Now, around the same time, the Packard Motor Car Company introduced an innovative system called the weather conditioner, which was released in 1939. This system combined an air conditioner and a heating system into a single unit, utilizing heat pump technology. Now, the system allowed users to cool or heat their vehicles and or homes as needed, providing year-round comfort. So all the way from the early 1920s through the 30s, we started really working on the development of heat pump technology to where now we've got it to where we can have both heating and cooling in several different applications. And this was a long time ago. To have this type of technology that long ago is incredible. Now, as that technology began to advance more and more and more, heat pumps found their way into various applications. In the mid-20th century, heat pumps began to be utilized in washers and dryer systems, as you can see to the bottom left here, allowing for more efficient drying by utilizing heat pump cycles to recycle and reuse the heat. Now, in the realm of residential heating and cooling, heat pumps gained significant popularity. These systems extracted heat from the outside air or ground and transfers it into the house during colder months, providing heating. We'll talk about that here shortly. During our warmer months, the heat pump cycle can be reversed, extracting heat from the indoor air and releasing it outside, which effectively cools the home. Now, this dual functionality makes heat pumps highly efficient and environmentally friendly alternative to traditional heating and cooling systems. Now, we can also see to the right there, from across from the residential heating and cooling applications, that pool warmers or pool heaters, pool water heaters, also are being utilized, also are utilizing heat pump technology. And when you take the ambient air or extract heat from the ambient air outside, heat pumps embedded into pool heaters really reduce energy consumption compared to conventional pool heaters, which does not contain a heat pump system inside. So now that we've had a little brief history on where our heat pump systems have come from and how far we've gotten, let's take a look into how heat pump systems work. And what we're going to do is we're going to take a look at an air source heat pump, which is one of the more common heat pumps out of three that we'll be talking about today. Now, air source heat pumps, as the name suggests, extracts heat from the surrounding air to provide both heating and cooling. And it works on the principle of the refrigeration cycle. Now, we're going to do a breakdown of that refrigeration cycle by identifying the four major components involved in the vapor compression cycle. Now, we can see on screen here to the left, we've got our air source heat pump, and you can see identified in that image there are four main components that we want to pay attention to. This is what allows us to go through the vapor compression cycle. We're going to have our evaporator, we're going to have our condenser, we're going to also have our compressor, and what's called an expansion valve or metering device. Excuse me. Now let's start off at our evaporation point or our evaporator. And the heat pump contains a refrigerant of some sort, or we call it a medium, which typically is a fluid with a low boiling point, such as R410 alpha, which is probably going to get phased out here soon. So R410A is a refrigerant which is commonly used in our refrigerant systems or air conditioning systems. Now, the refrigerant that is in our evaporator absorbs heat from the outdoor air through an evaporator coil. As the refrigerant evaporates, it turns into a low-pressure gas. So what I want you to think about when you think of evaporation or the evaporator component of the vapor compression cycle is low-pressure gas. If you remember anything, remember that. Now, refrigerants with very low climate impact are being utilized in some of these different systems today, such as CO2, isobutane, propane, and some applications are utilizing ammonia. Now, that's just a side note there. We'll talk a little bit more about refrigerants as we go deeper into our presentation. Next up is our compressor or compression. The low pressure gas that we have now had through the evaporator is then compressed by a compressor, which raises the temperature and pressure. So when you compress that gas, it now raises the temperature and the pressure of that gas. Moving from our compressor, after we've increased the pressure and temperature of that gas from the evaporator, we're going to go to the condenser where we'll have our condensation happen. The high pressure, high temperature gas that's coming from the compressor passing through a condenser coil is then rejected out into the ambient air. So heat from the compressed refrigerant is transferred either to indoor air or water. Hold that thought on the water, but stay with us on air for right now, which releases it back into the building, causing the refrigerant to condense back into a liquid. So at your condenser is where you're going to have your condensation. So it all kind of makes sense when you think about it. Evaporator, evaporation, condenser, condensation, condenser, high pressure, high temperature, evaporator, low pressure, low temperature. And then lastly, we have our expansion device or metering device. And this is where the high pressure liquid refrigerant, which is coming from our condenser, it flows through an expansion valve or metering device where the pressure is now reduced. We want to reduce that pressure going back into the evaporator. Now, this pressure drop allows the refrigerant to return to its initial low pressure state, and this prepares it again for evaporation stage and restarting that cycle all over again. So by cycling through these different stages, air source heat pumps extract heat from the outdoor air and it transfers it indoors during colder months for heating purposes. And in warmer months, it does the exact opposite. And that happens by use of a three-way valve, which I'm not too sure we get into in this course, but in our advanced course, we do talk more in depth about the three-way valve and how you go from heating to cooling utilizing heat pump systems. Over to the right, we can see we have an image there for water source type heat pumps. Just going to touch on this briefly because we do go into the types of heat pumps that are available out there today, or the three most common types of heat pumps. But water source heat pumps utilize a different type of heat exchange medium, such as a nearby lake, river, or well to transfer the heat or have your heat exchange. These systems offer excellent efficiency and are ideal for much larger scale applications. Just touch on it really quickly because we are a little bit behind schedule, but I do want to get this information across to you as far as the water source a little bit more in depth for those that are interested. But you have similar components to your air source heat pump when dealing with water source heat pumps. You have your water loop. You still have an evaporation and condensation component to your water source. You also have water circulation and heat distribution. So when talking about your water loop, this consists of supply and return lines, and it circulates the water between the heat pump and the heat source or the heat sink, which acts as the body of water. That water loop acts as the heat transfer medium. When you're talking to your evaporation and condensation, as far as water source heat pumps, it's similar to air source heat pumps. Water source heat pumps utilize the refrigeration cycle, but more indirectly. The refrigerant evaporates in the evaporator coil, absorbing the heat from the water source, which is the medium we're going to use for heat transfer, and then condenses in the condenser coil, releasing that heat to the water loop, which is what we're trying to do if we're going to look to either, depending on your mode, release heat back out so that way it's cooler, or absorb that heat energy from the ambient air to make hot water or make a room or zone warmer. You also have water circulation, and this is done by pumps. Pumps circulate the water between the heat pump and the heat source or the heat sink, meaning that water resource, facilitating that heat transfer. And then you have heat distribution. The heat pump's condenser coils transfer heat to the building's heating distribution system, which can involve some sort of a forced air system where you have mechanicalized motor systems that are now have fans attached to them that can move that air to wherever you require it. So water source heat pumps allow for efficient heat transfer between the heat source or the heat sink and the building. So heat source, meaning that body of water, lake, ravine, somewhere where we just have an abundant source of water that we can utilize in order to use a water source heat pump system. I did say we were going to touch on the types of heat pumps that are available out there, and there are three kinds that we're going to touch on today. We've got our air source heat pump, which we've already touched on just a little bit. We've got our water source heat pump, which we kind of dived into, and our ground source heat pumps, which are also known as geothermal heat pumps. We'll start with our air source heat pumps, touch on it a little bit more. Once again, these air source heat pumps are the most common and widely used type of heat pump. If you do have a heat pump at your home, it's probably going to be an air source heat pump. Now, the way that these systems work is that they extract heat from the surrounding air to provide both heating and cooling. So what that simply means is that the system sitting outside, if we are in heating mode, what's going to happen is the system is going to extract the heat from that ambient air or that outside air. So it could be 10 degrees outside. There is heat energy in the air. So what that heat pump does is it's looking for whatever little bit of heat energy is in that air, and it's going to pull it, and it's going to take it, and it's going to transfer it where we need it or where it's needed. Now, your outdoor air is used as the heat source or sink, similar to the water source systems where your body of water, your lake, is used as the heat source or the sink. Now, air source heat pumps utilize a refrigerant, once again, which circulates through the system and undergoes that refrigeration cycle, extracting and transferring your heat. Now, some advantages of air source heat pumps are that they're relatively easy to install, requiring minimal excavation or modification to the property. They're typically two components, one inside, one outside. You'll typically find your inside system in a closet, a garage, a basement somewhere, and your outside system sits on a slab directly outside the residence or property. Heat pumps that are air source are cost effective, and they are suitable for a wide range of climates. However, the efficiency can be affected by extreme temperatures. So I like to throw this little point out there that when I used to be in the field a lot more than I am now, roughly 15, maybe 20 years ago, exactly, we did a job where I was installing heat pumps on a camp at a military site, and that winter, this was in San Antonio, Texas, that winter dropped, the temperature dropped, and this is when heat pumps were at their early stages, early beginnings. So when I worked with heat pumps at that time, you were not able to get a heat pump to operate below 32 degrees Fahrenheit. You would have to have some sort of auxiliary or emergency backup heat working that system, so that way you can offset when you're unable to utilize the heat pump system in itself to produce heat for the rooms. So you'd have to use some sort of auxiliary or backup. Today, due to the modifications with the refrigerant that we have or the advancements in the refrigerants that we have today, we now can utilize heat pumps below 32 degrees Fahrenheit and in much colder climates than we could 18, 20, 25 years ago. So some considerations you want to have when talking about air source heat pumps in colder climates: the air source heat pump may require supplemental heating during very low ambient temperatures. Next, we have our water source heat pumps, and these are once again similar to our air source heat pumps, but it is utilizing a medium for heat transfer, which could be a lake, a river, or a well. These systems are highly efficient and particularly suitable for large-scale applications. So you're using water as your heat source and sink. Water source heat pumps extract heat from the water source. So wherever your water source is, just like with air source heat pumps, it could be 10 degrees outside. We're going to find that heat in that 10 degrees, and we're going to apply it where we need it. Same with the water source. We're going to take that water source, and it could be 60-degree, 50-degree water from a lake, And we're going to find that heat content inside of that water, and we're going to extract it to where we need it. And that's known as the heat source or the sink. And this is done, once again, through a water loop, utilizing pumps that will make that water loop continuously go until it is no longer needed. Some advantages of using water source heat pumps is that they offer excellent efficiency due to the relatively stable temperature of water sources. They can provide both heating and cooling, and their performance is not significantly affected by outdoor air temperature fluctuations. So if the air temperature outside is up, down, round and around, it won't affect the operation of a water source system, because that water source is typically going to maintain a certain temperature throughout. Some considerations when working with water source heat pumps is that they require access to a suitable water source. So this might involve some type of regulatory consideration where you may have to deal with permits and obtaining permits in order to do this. But something that you must remember is that adequate water flow and the quality of that water must be maintained when utilizing these different systems. You want to make sure there is no environmental impact when working with a water source heat pump system. And then lastly, we have our ground source heat pumps, which are also known as geothermal heat pumps. And these systems utilizes the relatively stable temperature of the ground or the earth to transfer heat. So there is heat content or heat energy in the ground. And before I jump further into the ground source heat pumps, just want to throw this out here again. So your air source heat pumps, you're going to be obtaining heat energy from the air. Your water source heat pumps, you're going to be obtaining heat energy from the water. Your ground source heat pumps, you're going to be obtaining heat energy from the ground. And like I mentioned earlier, the temperatures in Earth are relatively stable when looking to transfer heat. These systems are highly efficient and environmentally friendly. Ground source is what you're going to be utilizing as your heat source sink. Once again, it's extracting the heat from the ground during the heating mode and rejecting heat to the ground during the cooling mode. These types of systems utilize a ground loop system, which consists of pipes which are buried underground to facilitate that heat exchange. So the loop configuration, a little similar to your air source and water source, but ground source heat pumps employ these loop configurations, including vertical loops, horizontal loops, and pond lake loops. And the type of loop that you utilize depends on factors such as your available space, your soil conditions, and also local regulations. You want to be very, very familiar, and not just familiar, but you want to be very careful when choosing ground source as your heat pump source, because there are several things that come with that. We'll get into that here shortly. But advantages of ground source heat pumps are that they offer exceptional energy efficiency and can achieve high energy savings. They're not affected by outdoor air temperature fluctuations, making them available and suitable for various climates. And your ground source heat pumps have a longer lifespan and require much less maintenance than the other two that we spoke of earlier. Now, considerations for ground source heat pumps is that the installation of ground source heat pumps involve excavation and burying the ground loop system, which may involve costs as far as upfront costs that are pretty high, and also site considerations. So proper design and sizing, as well as thermal conductivity of the soil, are crucial for the optimal performance. There are places and regions where you absolutely cannot do a ground source heat pump system because the ground is unstable and it cannot be used anywhere where you have a lot of earthquakes. Certain regions in California might not be such a great spot for ground source heat pumps, just due to the fact that you may have those disturbances in the ground. So we just spoke about the three types of heat pump sources. We have air source heat pumps, water source heat pumps, and also ground source heat pumps, which offer distinct advantages and considerations among each three. Depending on your application, you will make a determination on which one of these different sources you're going to use. And you definitely want to make sure you have that research done when seriously considering a ground source or geothermal heat pump system.